Newton's gravity understanding was enough to get us to the moon. Ever wonder if we really get what time is? Newton's discovery is more than just an idea. It's a key that might show us the secrets of the universe, a cosmos wilder than we thought possible. How does Brian Cox's idea change what we think about time? And what could it mean for how we see things? Let's check out Brian Cox's cool idea about what time is in the cosmos. There are puzzles to solve, a lot having to do with time and gravity, both big parts of our lives. Imagine a world where time can slow down or speed up, where gravity isn't what we believe it is. This is where Albert Einstein's relativity theories come in. Einstein gave us a new way to look at the universe with his relativity theories. His work let us see how time acts in different places, like when things move super fast. It started in the early 1900s when Einstein shared two ideas, special and general relativity. Special relativity from 1905 changed how we see time and space. Simply, it says the rules of physics are the same for everyone who isn't speeding up, no matter how they're moving. This idea brings up things like time stretching or slowing. A way to explain time change is the light clock. Imagine you're in a spaceship going super fast. Inside, there's a light beam bouncing between two mirrors. Physics says light speed stays the same for everyone. So, the light seems to make a longer path for someone outside the ship. The time it takes the light to travel this path should be the same for both people, inside and out. But since the path is longer for the person outside, it looks like it takes the light longer to finish its trip. This time difference is what Einstein called time change. Time goes slower for the person moving compared to the one standing still. So time acts different based on your speed. Knowing how things change when they move fast isn't just a thought. Scientists use machines like the Large Hadron Collider to push particles close to light speed. When things move this fast, we have to think about time in a special way to get correct predictions. Einstein shared special relativity in 1905, and it flipped how we get the universe, mostly about time and movement. This idea goes against what we might think. It says physics rules are the same for everyone, even if they're not. Still, this is different from what we feel, where we think if something's moving and we add speed, it just gets faster. But Einstein says there's a top speed, the speed of light. With this in mind, things that happen at the same time for us might not look that way to someone zooming by. Another idea from this is length getting shorter. This means something looks shorter in the direction it's moving when seen from a still spot. Also, there's the equation EMC caret superscript 2 showing energy and mass can change into each other. This is key for seeing how tiny particles act when moving fast and for explaining stuff like nuclear reactions. In real life, special relativity isn't just a thought. We depend on it in tech, like GPS. When GPS satellites send signals to your device, they're moving. Because of this, time acts a bit different for them. If we didn't think about time changing in our GPS math, your location info would be way off. So, special relativity teaches us time isn't always the same. It depends on how things are moving. This messes with how we usually see time and space. It's like our usual take on the universe is a bit wrong. Time isn't set. It's changed by movement. Some basic ideas like light speed being steady and how energy and mass connect have been proven many times. But there's more. Einstein's general relativity from 1915 goes deeper into how gravity and the universe's structure connect. It changes the usual idea of gravity is just a force that pulls things. Instead, it says gravity happens because space and time are bent. It's like saying, gravity isn't a force. It's just how things move in the universe. For Brian, general relativity needs thinking of the universe as 4 parts, 3 space and 1 time. Big things like stars, planets, and even us bend space and time around them. This bend is what we feel as gravity. Imagine space-time is a big, stretchy sheet. When something heavy, like Earth, is on it, it makes a dip. If you put something smaller like a ball near Earth, it rolls to the dip. This is like how things act with gravity, not because of a force, but because space-time bends. General relativity explains how things move in our solar system, like planets circling the sun. You can guess the paths these planets take, like how Earth circles the sun. This is different from the old idea of gravity just pulling things together, which couldn't explain planets. Well, the new idea is space and time are bent like a bendy fabric which fits better with what we see. An event showing general relativity was right happened during a solar eclipse in 1919. Sir Arthur Eddington led a team to watch how light from stars bent as it passed the sun. The theory said the sun's weight would curve the starlight a bit. The watchings proved Einstein was right, showing the theory was good. Just like movement can change how we see time, gravity affects time too. Where gravity is strong, time goes slower than where it's weak. So, if you stood near something heavy, like a black hole, your clock would go slower than one far away from the heavy weight. General relativity brings up black holes, spots, where gravity is so strong even light can't get away. The edge of a black hole is called the event horizon, and it's where there's no going back. Once something crosses this edge, it's pulled into the black hole forever. Einstein's general relativity has big effects on the universe's structure. He first added a term called the cosmological constant to his equations because he thought the universe didn't move. But when he found out the universe is growing, he called this a big mistake. A growing universe is key to the Big Bang Theory, which tells how the universe started. Another idea of general relativity is gravitational waves. These are bends in space and time caused by heavy things moving fast, like when black holes join. In 2015, scientists at LIGO spotted gravitational waves, adding proof to Einstein's theory. Over time, scientists have done tests to check general relativity, and it's always been right. Watching planets, light bending, or spotting gravitational waves, general relativity is a good and sure idea. Saying gravity is a myth might sound wild since we feel it every day. But in physics, it's normal to question and think about old theories. Scientists like Brian often wonder about usual ideas. In gravity, some have new ideas. One theory is modified Newtonian dynamics, or man saying gravity acts different at low speeds, mostly in galaxies without dark matter instead of unseen matter. Man says gravity gets stronger at slow speeds. The talk on gravity also has dark matter and dark energy added to explain space stuff. Some say these ideas might not be needed, and other thoughts can explain what we see. Some scientists who don't agree with Einstein's gravity look into stuff like theories with unknown particles or forces that could change gravity. It's good to know that in science, new ideas aren't just thrown out. They're tested to see if they hold up. For example, Einstein's idea of time is a 4-part thing where time travel is held back by light speed has been looked at with ideas like wormholes. Stephen Hawking's chronology protection makes time travel into the past unlikely. In physics, new tests and watchings aim to see if these new theories can explain gravity in a way that fits what we know. But many ideas haven't really replaced the known rules of gravity. Questioning ideas is key for science to grow and get a better understanding of the universe. In gravity theories, general relativity is still the most important. Even with new ideas, it keeps doing well and explains stuff like planets and light bending. General relativity lasts because it's simple and fits with a lot. Einstein's special relativity says time can change based on your speed. Let's see how this hits real life, mostly in space. Moving in space is fun, but hard, because space is big. Light speed is the fastest, so moving between stars is tough even with tech. To get how time changes when moving in space, think of the twin thing. One twin stays on Earth, and the other takes a fast trip to a far star. When the space twin comes back, they find they've aged slower than the Earth twin. They've moved into the future. Time is big for space travelers. The longer the trip, the slower time moves. If astronauts went to close stars, where time slows a lot, they'd age slower than people on Earth. This might sound like a story, but it's real. Imagine humans sending people to a far star. The trip could be years. Even if they go fast, the astronauts would feel time slower because of time change. But from Earth, more time would pass. Time change hits too. Computers and communication on ships have to think about time change to work, right? Space moving his body problems like being alone, getting hit by space waves, and being far from Earth for a long time. In daily life, we see time change. In GPS needs the right signal times from satellites. Since these satellites are moving, they experience time dilation. So, it's important to include it in the calculations for the readings to be accurate. Not thinking about time change would mess up driving. Now, why do we only go one way in time? Time controls our lives, going from past to now to future. This one-way trip is part of us. But why? To get this, we look at entropy. How messy things are. Entropy, tied to time's direction, tends to grow as time goes, pushing time to go one way. The second law of thermodynamics says entropy will grow or stay the same. In a closed area, entropy likes to grow. It never goes down by itself. Time as we perceive it is tied to the idea of entropy. Entropy, a rule in thermodynamics, measures the level of disorder within a system. The second law of thermodynamics says that in a closed system, entropy tends to grow over time, leading to a change from order to disorder. This principle not only tells the behavior of physical systems, but also a way to understand time. To see this, let's look at a sandcastle. Sandcastle is a state of low entropy by a high degree of order. Over time, because of natural forces, the sand castle will become a sandpile, a state of higher entropy. This change shows the natural tendency of systems to move towards greater disorder, reinforcing the idea that time flows in one direction from past to future. Building upon Einstein's theory of general relativity, gravity is how spacetime is curved by mass and energy. Massive things like stars and planets warp spacetime, and this curvature tells the motion of objects, including light. This changed our understanding from viewing gravity as a force acting at a distance to seeing it as the result of spacetime geometry.